that we can draw a black box around the whole process. Then we have stream 1 coming in here, and then streams 5 and 7 leaving. Everything else is recycling here. So stream 1 coming in, streams 5 and 7 leaving. So if we have 100 kilograms per second here and 60 kilograms per second here, there must be 40 kilograms per second coming out here. So m.7 we expect a 40 for, and let's look at that. So if you look here, m.7 is indeed 40 kilograms per second, so that's correct at least. There are a couple of other relationships we have. If we go back to the problem, you can see here that we've specified that K3 and K4 are 0.5, and so m.5 is a half m.6. And let's look here. m.5 is this one, and then m.6 must then be twice that. So m.5 is a half m.6, and that is correct over there. And you can check that for the other split ratio as well. m.9 is twice m.10. So it's important to go back and look at the results and try to figure out, does this agree with my problem statement? Have I found a feasible solution when I've posed it here? Right? Remember, in issuing these statements, we should always regard these things with some doubt that behind this inversion command, that we know that the computer is going to do some rounding off at some point, that any algorithm will have particular restrictions in the sort of accuracy it can deliver, and so we should always go back and check, have those shall we say inaccuracies crept through to affect our results significantly. And according to the quick look that we had, according to the what we understand about this problem, we don't see major numerical errors here, so we can look at this result with some confidence. So it is important to go back, look at your results, and make those kinds of comments, and do that kind of mental, you can say, data reconciliation. So I had made the comment that matrix inversion was a computationally relatively expensive way to do this, that more correctly we should use LU factorization, and of course we can compute that using the LU command, and I did cover the LU command in the matrix video lecture, but let's just factorize it here. Remember that the LU command has the syntax that we will return the lower triangle, the upper triangle, and the permutation matrix in those positions if we ask for LU of the matrix. So let's write it here. Well, right, let's write it here. L, comma U, comma P equals LU of A. All right. Remember, that's where we stored our matrix A, and we can see here that L looks like this. The lower triangle is like this, the upper triangle is like that, and the permutation matrix is like this. So let's just check that LU has returned for us the right sorts of matrices. So L times U should be equal to the permutation matrix times A. Right, I'm just subtracting these two. If these two are the same quantity, then we should get a matrix of zeros. And so we don't get perfect zeros, we get extremely small numbers, right? That's limited by the computer's precision, but this is close enough. These are numbers times 10 to the minus 15, so we regard L times U as being very close to P times A. So indeed L and U are factorizations, the lower and upper triangle factorizations of the matrix A. And I'll leave it to you to use those matrices to then solve for the mass flow rates m dot. Right, so just to summarize what we've looked at here, creating the matrix might look somewhat tedious, and it certainly was the case when looking at the smaller problem, when there was just a single node and 3 streams. Then it was in fact easier to just solve that by hand. But for larger systems, it is actually far more efficient to compose this as a system of as a vector matrix system, and to solve that by inversion or ALU factorization, where for larger systems ALU factorization will be much more efficient. Right, we note that ALU factorization does have a limitation that if there are zeros on the diagonal, then we have to reorder the matrices, and we are fortunate that in Matlab there is a permutation matrix that is output with the solution, so that we can handle the matrix reordering quite easily. Right, now this issue of having zeros on the diagonal is not the same as the matrix being close to singular. Right, if we have any two rows that can be shown to be a linear combination of any other rows, then that means that some of our relationships are redundant, right? That we have some repetition in what we're saying. It might be the case, for instance, that if we had added as an equation, let's say on looking at the system, we decided we only have 6 relationships, and instead of trying to obtain additional information, let's say we tried to get additional information by finding more subsets of this process. So let's say, as we mentioned earlier, let's say we drew a big black box around this, and we said the stream 1 coming in was stream 5 and 7 going off here. Although that appears to give us another equation, that equation is actually a linear combination of these other equations. In other words, you can combine these equations to obtain that same result. And what that means is that this matrix will be singular. In other words, it won't be invertible, and so we won't be able to get to a solution. Right? And physically what this means is we don't have enough relationships. There's still a degree of freedom in the process, and so unless we have additional relationships like what we have here, we don't have enough information to come to a unique set of mass flow rates. So when that happens, we do correctly get a complaint from Matlab, but there are situations where we don't get such a complaint, and that happens when the matrix is ill-conditioned, and we'll look at that in the next video lecture.